Alright, you there, young man. Now, I'm looking for wood. And the wood I need has to be cheap and strong. Because I'm using it to make a ramp. Alright? And I want to be able to jump on this ramp. And I'm a pretty big guy, so you know. Because I'm so big, I need a strong ramp. But I'm pretty goddamn broke. Alright? Now, I see two wood here. Which one will be the best for me?
This top one here is called Kiln-Dried. And what it means is pretty much it's been baked in the oven, which lowers the moisture content, which raises the strength. And the moisture content would be 12.
Okay.
12%.
Okay.
Your bottom one, you have what's called green. That means it's freshly cut. It's freshly cut and it's about 37% moisture content. That means it's going to be a bit weaker. However, this one is a bit more expensive than the green.
Now this one's the cheaper one. And it's fairly strong, but not as strong as this one. And this one is more expensive. Okay. Young man, I'm gonna make a proposal. I want both. Take it from my cart. Let's go.
Hey, what's going on, man? Interesting. You know what? Let me get back to you on that. Alright, I'll call you back in a bit. So a buddy of mine was calling me. He went to Home Depot. So he asked this guy, one of the employees, he was saying, well, I need a wood that I could play around with. What's the strongest content? One's Douglas Fir, and one is Kiln-Dried. Do you know what kind of wood would be stronger?
No, not really.
Should we search it on YouTube?
Sure. They have pretty much everything on it.
Oh yeah, they do. Every tutorials, every discussions.
Hear those sleigh bells jingling, ring, ting, tingling too. Come on, it's lovely weather for a sleigh ride together with you.
Ho, 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 and welcome to our YouTube channel. My name is Yulia Artishuk. And I'm Katie Culbertson. Today, we'll be making predictions of the flexural strength of a low-moisture kiln-dried Douglas Fir beam and a high-moisture green Douglas Fir beam with two equidistant compressive loads applied perpendicular to the wood grain. Our guest speaker, Sam Rojas, is going to take us into the lab and show us this experiment hands-on. I hope you guys enjoy. Stay tuned. Let's go. Now we'll be calculating our predictions using equations that we've learned in our structures lab.
Jingle bell, jingle bell, jingle bell rock. Jingle bells swing and jingle bells ring. Snowing and blowing up bushels of fun. Now the jingle hop has begun. Jingle bell, jingle bell, jingle bell rock. Jingle.
Katie, I think I'm done. I calculated the max load for the Douglas Fir green one and for the 12%. But are you taking into account the actual moisture content of the wood beams? You're right. You know what? We can use that book that Sam talked about. We can use the Wood Engineering and Construction Handbook, 2nd edition, and we can account for the different moisture contents of the wood beams. Awesome.
Time and jingle bell time, dancing and prancing in Jingle Bell Square. In the frosty air, what a bright time, it's the right time to rock the night away. Jingle bell time is a swell time.
Here is a diagram of our beam. As As you can see, there's a 36-inch span. The load will be applied 12 inches from the first roller, and the other load will be applied 12 inches from the second roller. From our calculations, we determined that each roller will have a reaction of P/2. To find the maximum shear, we decided to make a shear diagram. Here we calculated we used our reactions and our loads in order to find the shear diagram. So it goes up P/2 over a distance of L/3 and back down. Then it goes L/3 without any loads being applied or reactions. And then there is a negative P/2 at 2L/3, which takes us to the end of the beam and where it closes to 0. From our shear diagram, we calculated our moment diagram. We needed to find the maximum moment in order to find our maximum load in bending. So for our maximum moment, we use the shear diagram to calculate the area here. Area 1 shows how the area was calculated in order to find our maximum moment. So the maximum moment was calculated to be PL/6. And this is the value that we're going to be using in our equation to find our maximum bending stress for each of the two beams. To calculate the maximum load of each beam before it fails in bending, we can use the stress equation. The stress equation is equal to F is equal to the maximum moment times the distance from the neutral axis divided by the moment of inertia. We can rewrite this equation to get that maximum load here, and we would apply F. We would use the value from chapter 4 in the handout in the modulus of rupture column, and we would use the base and height. We would have a cross section of 3.5 by 1.5. Like 3.5. That would be our cross section of our beam. And for our green Douglas fir, we would have a max load of 1,684.4. And for the kiln-dried, we would have a maximum load of 2,756.25 pounds. Now, if we were to take into account the moisture content, because this is presumed to be 37% and this is presumed to be 12%, we can use this equation that is found in the Wood Engineering and Construction Handbook. This is the equation, and we would apply the same numbers that we found. The 2,756 would be this load, and the 1,684 would be the PG load. And this would give us a number for the 31% moisture content of 1,263.8. And for the 17%, which is the kiln-dried, we would have a max load of 2,244.93 pounds. In order to verify that our beams are going to be failing in bending rather than shear, we did some calculations to determine what loads they would fail in shear. So we used the shear stress equation up here, which is 3V over 2A. And we rewrote the equation in terms of the maximum load. So the maximum load equals the shear stress times 2A over 3 times 2. So for the kiln-dried wood, we got the value for shear, the maximum shear, in chapter 4 of the handout. We also got the maximum shear in the handout for the green wood. The maximum shear stress, or maximum shear load for the kiln-dried wood is going to be roughly 9,000 pounds. And the maximum shear load for the green wood is going to be 6,580 pounds. When in comparison to our bending equations, maximum stresses, they are much higher. So we can be assured that the beams will fail in bending rather than shear. Now let's take these calculations and take them to lab with Sam Rojas.
Give it up to Sam!
My name is Sam. I'm the lab technician. I'll be the one testing your beams. And first of all, thank you for letting me spend some time in your famous YouTube channel. And if you just follow me, we'll get the testing done right away. For the dry beam, we had a Flexural failure at a load of 2.657 kips. For the greenwood beam, we had initial cracking at a load of 1.5 kips. This is shown in the green area. As you could see, we had knots on the side and on the bottom of the beam. Our maximum load of 2.173 kips occurred in the blue area. At this point, we had flexural failure. After this, we had a compression failure at the very end. So these are the your predictions. This is what you were predicted. When we actually went into the lab, these are the numbers that we got for the failure, which was in flexural failure. And when we compare the ratios, we get a 1.72, and the second one, which was much closer at 1.18.
Sam, why do we have these ratios? Could it be due to the errors in the beam?
Yes, I noticed that one of the beams, the first one, you had a visible knot at the bottom. And probably the biggest source of error is that's just the nature of wood. You're never going to have the perfect sample. The equations that we have, they're within a range, so you're never going to have a perfect answer.
Okay, great. Thank you, Sam, for coming on our show. We're pleased to have you.
Thank you for having me.
And stay tuned for our January issue.
Bye.
Come on, it's lovely weather for a sleigh ride together with you. Lovely weather for a sleigh ride together with you.